Okay, so this talk we are going to discuss discrete partial, the discrete analogs of the partial. Now, discrete basically means that the input variable is not varying continuously, but it can take a certain discrete bunch of values just separated. Now, continuous is sort of a situation where the variable can move over the real line. The single variable is just where it move over the real line. Discrete in the single variable case usually means it can take a bunch of values which are separated. And I'm going to take the simple case where the values are positive integers. N is a positive integer, so the function is defined on 1, 2, 3, so on. Now, in the continuous case, we define the derivative as this limit of a what's this thing called? Difference.
Partial.
No, this limit thing whose limit we are taking. It's a quotient of difference. So it's a difference quotient. Okay, and the reason is that the numerator is the difference of the function, while the denominator is the difference x plus h minus x. And that's where you get h here. X plus h minus x. Now, if you are doing a function, so this is the function of continuous variable. If your function is a function of positive integers, then it doesn't really make sense to take a limit, because if your x is here, there isn't anything close to x. However, you can take the closest which you can get to the right of x is x plus 1. And in that case, you can try to take the difference quotient of f between x and x plus 1. And that would be f of x plus 1 minus f of x divided by
1.
Why 1? Because it's the difference of these two is 1. Right? So it's divided by 1. But division by 1 doesn't affect anything. That's why I didn't write that down. Okay, so just f of x plus 1 minus f of x. Now I'm going to abuse notation a bit and just use the same notation as for the continuous thing here. Okay, because, I mean, it's not actually the same thing. If it's actually a continuous function, the continuous is different, but I just use the same notation just so you can see the parallel more clearly. So this is sort of like you're taking the derivative, but you're not really taking the limit. You're stopping as soon as you get 1 away, and then you just take the difference quotient. So now I'm going to consider a function of two variables. And I'll assume that both variables can take all positive integer values. It's a function, real valued function of two variables. So it's not, this f is not the same as this f or this f. They're all different. And it's a function of two variables. So what is going to be the partial in this sense? Well, the technical term for this is a forward difference operator. But I'm just going to assume, like, call it the derivative. This is a discrete derivative. So what is this? Well, it's the derivative with respect to x holding y constant. So it's the function at x plus 1 comma y minus what?
F x comma y. X comma y plus 1 minus f x y.
Okay. Now, so what is f sub x of x comma y plus 1?
That will be f x plus 1 comma y plus 1 minus f of x comma y plus 1.
So it's the same as this. These are the same, except your y just gets split by y plus 1 everywhere. And what is f of y x plus 1 comma y?
It will be f of x plus 1 comma y plus 1 minus f of x plus 1 comma y.
Okay. Now we are in a position to do f of sub x, y, x comma y. So first, let's just think of the sort of what's happening. So it's this, right? First, we need to figure out what is f sub x of x comma y, right? And then we need to figure out what is like f of. So this is what? So this is f sub x of x comma y. So if I just think f sub x is my new function, then that y derivative of that is just that
Y
comma y
plus
plus
1 minus f sub x of x, comma y.
Yeah. Now I have both these expressions here, right? So I can get them here. It's f of x plus 1, y plus 1.
Minus f x, y plus 1.
Minus
f x plus 1 y plus f.
So you get a double minus, and so you get plus
x,
f.
y.
We have this here,
Yep.
whole thing. Okay, now let's say I want to do the other mixed partial. So fyx of x comma y. So this will be
F sub y, x plus 1 comma y, minus f sub y, x comma y,
so
y plus 1, y plus 1.
So these two answers are the same, right? These two terms are just flipped over in order, but they're the same thing. What really happens is that, and this is expected, because in the continuous case there was some theorem which told you that the mixed partials are the same. But in the discrete case you don't need any continuous assumption. It's just like mathematically the same. Now geometrically, sort of, if you think of these points, so here's xy, x plus 1y, x y plus 1, is that right? And x plus 1 y plus 1. You are to put a plus sign on these and a minus sign on these, and that's a mathematical way of thinking of this. But the basic reason you have plus on both of these is because you have two minuses here, right? Okay, so you have this plus this minus this minus this. So that's what the mixed, and actually so the discrete version of that theorem, which said that the two mixed partials are the same, is true, always true for this reason. So that's what the discrete mixed partial looks like. Now, why is this important? Well, this actually can help us understand in sort of a more clear way all that thing about matching and about negative matching and assortative matching. And the reason is that sort of if your f is actually a continuous function and you're just restricted it, are we okay? So if your f is actually a continuous function, you just restricted it in the discrete case, then this discrete mixed partial is related to the continuous mixed partial. Sort of, if the continuous mixed partial is positive, then the discrete mixed partial is also positive. If the discrete mixed partial is, if the continuous mixed partial is negative, the discrete one is also negative by something like the Lagrange mean value theorem, also, which relates these two. In the one-variable case, there's something similar in the many-variable case. What that means is, so if you remember, there was this whole like teacher-student pairing issue, right? And the question was whether putting the best student with the better student with the better teacher and the worst student with the worst teacher is better than putting them in a crossed fashion. Now you can see that actually sort of this plus this represents so the total utility or the total thing you get if you do the assortative pairing. Okay. So x plus 1 is the better thing and y plus 1 is the better thing. X and y are the less good things. Then adding these two gives you the total utility you get from the assortative pairing. And adding I should have used another. Doesn't really matter, but adding these two tells you what would happen. The red ones tells you what would happen if you use the other pairing, the non-assortative pairing. And so the sign of this thing is actually telling you whether this pairing is better than this pairing. And that's essentially the sign of the discrete mixed partial is therefore telling you how you should pair whether you should pair assortatively or negatively. And the reason why the continuous mixed partial was used instead of the discrete one there was because if the continuous mixed partial has a fixed sign, then the discrete ones will also have the same sign. Now let me just do a couple more. I'll just do the pure ones. F sub xx of xy. Well, I'll just write this down. It's going to be f of x plus 2y minus 2f of x plus 1y plus f of xy, and f of yyxy. Yeah, this thing you can try out and see if you get the answers. Okay.